In this lecture, we're going to be talking about data inferences, or in other words, we're going to be using the numbers to form a conclusion or to give meaning. We saw a hint of this in the last couple of lectures. We're first going to talk about the sampling distribution of the mean. Then we'll introduce the Central Limit Theorem. Then we talk about estimation and confidence intervals, and finally we top it off with hypothesis testing. Now the four topics here can be considered like the core theory of all the statistical tests that we're going to be looking through in the rest of this course. So these four topics are very important. This lecture is actually also very long, but for the purposes of dividing it up to classes, you can consider that this is actually two classes, and so for the next class you can actually stop after the Central Limit Theorem, or in other words, up to the checkpoints. The first bunch of checkpoints that we're going to look at, you can consider that to be the first class. So it's okay for you to stop after the first two topics and then continue on next week with the next two topics. But if you want to, go ahead and complete the entire lecture in one setting. It's okay. Now, we've looked at population distributions before, but now there's something new here, sampling distributions. And just a quick reminder, when we talk about distributions here, what we mean is like the shape of the histogram when I've collected certain data about a particular population. For example, I've collected the heights of a population. So when I plot it out on the histogram, the x-axis would be the values and the y-axis would be the frequencies or the probabilities. And so after I plot it out in the histogram, I can get a shape, a particular shape or the distribution of this particular population. And from there, I can make some kind of assumptions about it. For example, I see that it's normally distributed. So I know that I can make the assumption that this particular population follows a normal distribution, right? So that's what we mean by distribution. And that was, so far we've been looking at population distributions. But now we have a new idea here. The idea is there's also a distribution, but it's a sampling distribution. Now the purpose of introducing this idea of a sampling distribution is because of this fact. What we want to do here is we want to make inferences about a population based on samples. Now what do we mean by that? Think back to the previous lectures. If you remember, we're always interested in the population, a population of some kind. For example, let's say I'm interested about the population of men in Malaysia. Now that's a huge number of people. If I wanted to collect data about this particular population, it would be impractical. So instead, what do? Instead of collecting the entire population of men in Malaysia, I pick a sample. Let's say 1,000 randomly selected men in Malaysia, maybe 1,000 randomly selected men in KL, right? And based on measurements of that particular sample, I make some conclusions or some assumptions about the population as a whole. The correct term in this case is inference. So based on the sample that I collected, based on the calculations, the data about the sample, I make some inferences about the population as a whole, assuming that the sample is representative of the population. So, what do I know about the sample? I can calculate parameters, standard parameters about the sample, for example, the mean, the sample mean, x bar, right? This is very standard. If I have 1,000 samples, then the sample mean in this case is the sum of all the values divided by the sample size, in this case 1,000, so that's x bar. And this sample mean, or this sample parameter, they are estimates of the unknown true population parameters. In this case would be the population mean, or mu, right? So keep in mind, remember what we said, the population as a whole, that's the one I'm really interested in. I'm interested in the population's mean, right? Or some other parameter about population, but it's usually the mean. So I'm interested in the population mean, the population parameter, but I don't know it because it's impractical to calculate it. How would I calculate it? I'll have to measure every single individual in the population and divide by the total number of individuals in the population. Again, impractical. So what do I have? I have the sample mean, and I assume that this guy here tells me something about this guy. Notice I didn't say they're exactly the same, but I'm assuming that this guy tells me something about this guy. So let's have an example. Let's test out, let's say we're testing out this theory. Heavy smokers who quit will lower their heart rate, right? So we're assuming here, the theory here is that people who smoke, after they quit, their heart rate will go down. My target population is smokers, where I define smokers here as people who smoke more than 1 pack per day, right? But But obviously this is a huge population, so I'm going to collect data about a sample population, where the samples here are volunteer smokers who meet this criteria, meaning they smoke more than 1 pack per day. And these volunteers, I find them inside University Hospital. Let's assume that everything else is correct, meaning I've collected them randomly, right? And the parameter I am measuring here is going to be their heart rate. So in other words, I'm going to measure the heart rate of these volunteers in UH who smoke and who have agreed that as part of this study they're going to quit smoking. And after they quit smoking, I'm going to measure their heart rate again. And we're going to see whether there's actually a lowering of their heart rate, and to see whether this theory actually pans out, whether it's actually true. After I carried out the experiments, we discovered that the mean decrease in resting heart rate for 40 patient sample is 23 beats per minute. Now remember what we're trying to do here. We've collected data about 40 volunteers who smoked and that quit smoking. So we measured their heart rates before and after they quit. And we discovered that the mean decrease in their resting heart rate is 23 beats per minute. Now, ignore the fact that we are actually testing this theory of whether quitting smoking will reduce their resting heart rate for the moment, or it will reduce their blood pressure. And let's focus on another idea, which is this fact that when I collected 40 patients, I measured a mean of 23 beats per minute. Now obviously the entire population of smokers is much bigger than these 40 patients or these 40 volunteers. Now what happens if I don't stop here? What happens if I go out and collect another 40 patients, another random 40 volunteers, right? If I do that, if I go out and collect another 40 random smokers who decide they're going to agree and they're going to quit smoking, and I measure their decrease, do I expect to get exactly the same mean decrease in resting heart rate? Do I expect to get exactly 23 beats per minute as well? Right? Now, obviously, you don't expect it to be exactly the same. However, you probably would guess that if I do collect another 40 and I've done everything correctly, it's the same kind of patients, they're also smokers who smoke more than 1 pack per day, I get it from the same location, etc, etc, etc. It may not be exactly 23, but they are more or less the same. Now let's assume I collected yet another 40 and then measure their mean decrease in resting heart rate again. Would it be 23 again? No, it would be something else. So let's say I got 23, then I got 24, then I collected another 40, I got 25, I collected another 40, I got 21, and so on and so on and so forth. And I got a whole bunch of different sample means. So from the first group of 40 patients, I got one sample mean, and then from the next group of 40 patients, I got another sample mean, and then another group of 40 patients, I got yet another sample mean, and so on and so on and so forth. Now, based on all that, I think if you can realize that if I got one sample mean, two sample means, three sample means, I can calculate the average of all those numbers, right? Because there's a 23, there's a 24, there's a 25, there's a 21, and so on. They're just numbers, and I can calculate an average of them just by adding them all up and dividing by the total number of groups of 40 which I collected. And not just that, since I can calculate the average or the mean of those values, I can also calculate the standard deviation or the variation, right? So I can also calculate the variation of means from different samples to different samples, right? In each sample group that I collected, I calculated one sample mean. In the next sample group, I calculate yet another sample mean. If I collect a whole bunch of them, I can calculate an overall average of all the sample means. I can also calculate the standard deviation of all those different sample means, right? So we're getting multiple samples and then we compare. And how do we compare? We use the standard methods of measuring the arithmetic average as well as standard methods of doing standard deviation. We've seen that before. Now, all these different values, all these different sample means which I collected, I can also use them to form a new distribution. And this new distribution, I call it the sampling distribution of the means. Now remember, what is a distribution? The distribution is just the values on the x-axis and the probability or the frequencies on the y-axis. Now in the case of a population distribution, the x-axis were the values of each individual, right? These were the values of individuals, and the y-axis are the frequencies of all these individuals. So in other words, let's say an individual patient, if he quit smoking, maybe his resting heart rate went down by 20. Now, so he would be 20, he'll be one of the dots on the 20 on the population distribution. Now in this case, however, it's a sampling distribution. The x-axis is the sample mean, the value of the sample mean. So one of those sample means was one of my 40 patient sample. Now, it doesn't have to be 40 patients, it just so happens to be 40 patients in this case. So in this set, for this sampling distribution, the x-axis is all the different values of the sample mean. Okay, now remember, one of the sample means I calculated was 23, so that's one notch here. Then I got 24, so that's one here. And I got 21, that's one here, and I build it up just like how I build up my population distribution, and I end up with a sampling distribution. Okay, now a sampling distribution may be of any kind of statistic. It may be of mean, sampling distribution of the mean. It may be median, sampling distribution of the median, sampling distribution of the standard deviation, etc., etc., etc. Just now we were doing a sampling distribution of the mean, but you can imagine I could do one for the median as well. Again, let's say I had sample size of 40. Okay, let's change it now. Let's say I went out and did sample sizes of 30. In other words, I collected 30 people. I could calculate the median, so that would be the sample median value. Then I went go out and collect another 30 patients, and I could calculate a new median from there, so that would be the second sample median. Now collect another 30 and be the third sample median, and so on and so forth. I have all these different median values, all these different sample median values, and with all these different values I can plot yet another histogram, where the histogram's x-axis would be all the sample group median values, and the y-axis would be their frequencies or their probabilities, and that will form yet a new distribution. And this distribution, I would call it the sampling distribution of the median. Right? Now the defining features here, first of course, is what statistic of interest we are actually measuring here, whether it's the mean or the median or the standard deviation and so on and so forth. It must be random selection of the samples. That is clear. The size of the samples or the number of tests I'm applying for one particular sample group must be defined. So in other words, I can have a sampling distribution of the median, where in this case the size of the samples is 40, and I could have yet another sampling distribution of the median or the mean, right, where in this case the size of the samples were 20, right? And of course the defining feature of the sampling distribution is also based about the population being sampled in the first case. If the population being sampled, their mean or their average is roughly around 30, then I would guess that my sampling distribution would also have a mean around 30 as well, because the sampling distribution should reflect the population being sampled. This will become more clear later. Let's give a more concrete example about what actually is a sampling distribution and how I create one. Let's assume here that the physician is analyzing how long it has been since his patient's last checkup. And his question is, do they need annual checkup reminders? So let's assume here he has a population. Now population here meaning all the total number of individuals inside of our particular definition. In this case, this doctor is very sad. He only has 5 patients, right? So that's his total population. For patient 1, it's been 12 months since his last checkup. Patient 2, 13. Patient 3, 14, 15, 16, and so forth, right? And so this is population, but he being a lazy doctor, he decides that I don't want to measure the entire population, I want to measure samples. I just want to take samples. And so he's going to take 2 patient samples. Now, if he goes on and randomly picks 2 patients to create his sample group, how many possible combinations are there? Right? You can easily calculate that out. For example, assuming that we allow for duplicates here, right? He could have randomly picked patient 1 and then randomly picked patient 1 again. Or he could have randomly picked patient 1 and 2, 1 and 3, 1 and 4, 1 and 5, 2 and 1, 2 and 2, 2 and 3, 2 and 4, 2 and 5, and so on and so forth. Now you see there are duplicates happening inside here. 2 and 3 and 3 and 2 are obviously the same. But let's assume this is a truly random selection here, and I allow for duplicate selections. And so what's going to happen? Patients 1 and 1, 12 and 12. So if I calculate their sample mean, so remember this is one sample group here. The sample mean is going to be a 12. The second group, is patient 1 and 2. Their values here is 12 and 13. So their sample mean here is going to be 12.5. Right? Let's jump. Let's say patient 3 and 5. Right? Patient 3 and 5 is 14 and 16. And so for this particular sample group of size 2, their sample mean is going to be 15, because 14 and 16 divided by 2. Right? Now, all in all, there are 25 possible sample groupings. And remember, these are all the different sample means from these 25 possible sample groups. So what happens if I take these 25 different sample means, they're just numbers, and I try to form or plot a histogram, or try to see their distribution. That will be their sampling distribution, the sampling distribution of the means. This is the histogram for the particular population. Remember, my population only consisted of 5 people, where in which case X, the number of months, 12, 13, 14, 15, 16, there was only 1 each. So 1 patient here, 1 patient here, 1 patient here, 1 patient here, 1 patient here. The population distribution is square-shaped. This is not a nice normal distribution, it's just square-shaped. Now, there were, out of this population of 5, deciding to pick a sample size of 2, there were 25 possible sample groups. And so from those 25 possible sample groups, I calculated 25 sample means. And from those 25 sample means, they range anywhere from 12 to 16, right? Where 12 here would be me selecting patient 1 twice, and 16 here would be me selecting patient 5 twice, and everything else in between. Now when I calculate the histogram, or the distribution for the sampling distribution of the means, notice it looks a bit different. But of course, before even noticing it looks a bit different, understand how I even created this in the first place. I hope you see that this is just a normal histogram, right? A normal distribution, but in this case, instead of the x-axis being each individual patient, now the x-axis is the sample means, right? Or the x-bar. X-bar is the sample mean, number of months. Y-axis is the probability. Now, the population mean is 14. The sample mean, the mean of all the sample means, or the mean of this sampling distribution, which is made up of sample means, right? The mean of this sampling distribution is also 14. The variability of the sampling distribution is less than the population variability. Now remember, what is variability here? Variability is spread. Now, if you look at this population distribution, its variability is very wide, meaning it's very spread out, it's very even. However, for the sampling distribution, it's much more concentrated into the middle. It's much more concentrated around the mean, around the average. So the variability here is much smaller, right? So it's less than the population variability. And the shape of the sampling distribution in this case is approaching a normal distribution. It's starting to form a bell curve. Remember, we didn't start with a normal distribution. This population distribution is not normally distributed, and yet, even though the sampling distribution was only based on a sample size of 2, right? Just a sample size of 2, the sampling distribution starts to look like a normal distribution, right? Now, these ideas where the variability of the sampling distribution is less than the population variability, and this one where the shape of the sampling distribution starts to approach a normal distribution, these two facts are important ideas about sampling distributions as a whole when compared to their population distribution. So what was the point of doing all that just now? What's the point of calculating all this sampling distribution? Now you have to think about it this way. What was the point of calculating, of knowing the population distribution? Let's say I have the population distribution, meaning I have measured all the individuals inside my population, and I know my population distribution looks like this, and when I look at that, I say that, oh, this resembles a normal distribution, a theoretical form of the normal distribution, and therefore I can start to use this theoretical form to answer some questions. And a typical question might be, what is the area underneath the curve, right? Or what is the probability of me going out into this population and randomly picking an individual, and what's the probability of this individual, this random individual, having a, let's say it's a height, having his height less than 150 centimeters. right? And I can't do that because that's what the population distribution tells me. It tells me individual values on the x-axis, probabilities on the y-axis. And if I want to know probability of height or x less than 150, I'll just calculate the area underneath the curve over here, right? Now that was for the population distribution. Now let's say I have the sampling distribution, the sample distribution. So similarly, it is also a normal distribution. Let's say it looks like a normal distribution for now. And if I have that, then I can do the same thing. I can say, what's the probability this time of calculating, let's say, instead of going out and into this population and picking out a random individual, let's say I have a sampling distribution which was defined by sample size of n equals 30, right? It's a sampling distribution where all the sample means inside there came from sample groups of size 30. Now, if I have the sampling distribution of this particular type, that means that what I'm saying is that if I go into the population and I randomly pick 30 people, right? If I randomly pick 30 people, I can calculate the sample mean from these 30 people. And from this distribution, I can now say, if I go out and randomly pick 30 people, what's the probability of their sample mean being, let's say, 150 and below? And I can do that because I can calculate the area underneath the curve from negative infinity to 150, right? Because the area underneath the curve, once again, is the probability here. Now, remember, again, the probability, the population distribution is about individual values on the x-axis, and what it says is if I go into this population and randomly pick one individual inside there, what's the probability of he having, alright, let's change it now, what's the probability of he having a height that's greater than 180, and I can calculate that by calculating the area underneath the curve, or I'm integrating from 180 to infinity, or just look up inside the table. Now similarly, if I have a sampling distribution where the sampling distribution is defined of different sample groups of size 30, I'm saying that if I go into this population and I randomly collect 30 people, then what's the probability of me getting their sample mean of this particular bunch of people which I collected, of their sample mean being 180 and greater, right? And I'm doing the exact same thing here. I'm also integrating underneath the curve from 180 to infinity, because it is also a population, this is also a probability distribution. I said one probability distribution is of individuals, and one probability distribution is of sample means, or groups of individuals, not individuals themselves, but their groups. Okay. Now, what is the usage of this? Usage of this is, let's have a typical example of a study. If drug A actually provides no improvement over a placebo, then what do I do to test this? I want to see whether drug A works. So I would have two groups, right? One of these groups of patients will take drug A. One of these groups of patients will take placebo. And let's say drug A is a painkiller. So I'm going to see whether their report of the pain that they feel actually goes down. So whether they feel a decrease in their pain level. So I'm going to measure them, and I'm going to see what's the difference between the group which took the drug and the control group which only took the placebo. Now when I actually measure this, let's say I have a group of 30 patients, I'm going to, of course, when I have a group of 30 patients here, I'm going to see a difference between these two groups, right? The group which took the drug and the group which took the placebo. And when I carry out this experiment once, there's going to be an average difference in terms of their decrease in pain level. Now that's if I do the experiment once. If I had the sampling distribution for this particular experiment, where the sampling distribution means that each of the values on the x-axis is me having done this exact same experiment once, and then do it again, and then I get another value, do it again, I get another value, and I got this sampling distribution. Now ignore for the moment how I got this sampling distribution in the first place, right? Let's assume I have it. So assuming I have it, then I could answer the question, which is, if I were to do this particular experiment right? If I were to do this particular experiment and I know the sampling distribution already, if I do this particular experiment, what is the probability of me getting a particular sample mean? A sample mean, in this case, where it's the difference in blood pressure, or sorry, just now I was talking about pain, in this case it's blood pressure, between the test and the control groups as obtained in the study, right? So if I know the sampling distribution, what's the probability of me getting a particular mean difference between these two groups, right? And how could I do that? I would once again look underneath the curve. I would integrate from, let's say, negative infinity to this particular number, and I'll be able to get the probability of it, right? Simply from the sampling distribution. Again, ignore the fact of how I got the values of this sampling distribution in the first place. Let's just pretend that I do have it, and that's what I could use it for. We'll look at how we get it in a moment. Now, one last reminder before we continue on to talk about how we generate this sampling distribution in the first place, how we practically generate it. We saw how we theoretically generated previously. Now, the population distribution is a distribution of individuals. The sampling distribution is a distribution of sample means, right, or sample parameters. Usually, we are going to look at sample means, but it could be sample, median, sample standard deviation, and so on and so forth. Now, both of them are distributions. Both of them, you can think of them as histograms. And you can see their shape. However, in the case of the population distribution, the histogram here is made up of individual values. In the case of the sampling distribution, the histogram here is made up of individual sample means, or in other words, they're made up of groups of individuals. Each group then provides one particular value. In this case, usually it would be the group mean or the sample mean. Alright, each of those sample means forms one of the values of the sampling distribution, but at the end of the day, you still form a probability distribution. In this case, called the sampling distribution of the means. This brings us to this concept known as the Central Limit Theorem. And hopefully, this theorem explains just what we are trying to do with the sampling distribution in the first place. Now, if you look back at the sampling distribution, what we've been talking about, remember how do we actually create a sampling distribution in theory? Okay, in theory, how we create a sampling distribution is we go out, we collect one random group, one random sample group, we calculate the particular parameter we're interested in, and then we go out and collect another random sample group and another one, and we take all the parameters we calculate, and the different parameters we form a new distribution, and that distribution we call it the sampling distribution. Now, obviously, trying to actually create this theoretically perfect sampling distribution is very, very time and effort consuming. Remember the example we gave just now about the population of only 5 patients? The entire population only consisted of 5 patients. And yet, trying to create a sample distribution of size 2, of size group 2, we had 25 possibilities. This suggests, and it's true, that trying to create the perfect sampling distribution is actually harder than going out and measuring all the individuals inside the entire population as a whole. It's even harder. So if trying to measure the entire population is not practical, then trying to generate the sampling distribution is also not practical. So what then do we do? What we do is we use the Central Limit Theorem. Now, the Central Limit Theorem says if we have a sampling distribution, where the sampling distribution is defined of be made up of repeated sample sizes of size n. Now, this is exactly what I've been talking about previously. A sampling distribution is made up of a whole bunch of different sample groups, but all of them must be of the same size, sample size. And usually, we are trying to measure the parameter of the mean, right? But it could be anything else. So let's assume we have this. Now, what does the Central Limit Theorem say about this? It says that, starters, if I have this perfect sampling distribution, then the mean of this perfect sampling distribution, right? Or let's say the sampling distribution was of the sample means, so this would be the mean of all the sample means. Okay, sound confusing? But basically it's just the mean of this particular sampling distribution, the center value. Now, if I have this perfect one, then the mean of the sampling distribution is equal to the population mean, or mu, right? So if I have the perfect sampling distribution, the mean of that is equal to the mean of the population, right? Or the mean of the population distribution. Same thing, they're equal. So that's point 1. Point 2, the standard deviation of the sampling distribution. Now remember what is standard deviation? Standard deviation is just a measure of the spread of the distribution. Now the standard deviation of this sampling distribution is known as the standard error of the means, or standard error of the median, or standard error of the standard deviation, and so on and so forth. Usually standard error of the means, or just standard error, SEM, right? This is what's it called. The standard deviation of the sampling distribution is also known as the standard error. Now how do I calculate the standard error? Right? It can actually be approximated by this. Sigma divided by square root of n. Now what's n? N is just the sample size. In other words, if my sampling distribution is defined as being made up of multiple random sample groups, where each of these sample groups have a size of n, then I use the n here. For example, if it's n30, then the standard error here will be sigma divided by square root of 30. Which brings us to this. What is sigma? Sigma is actually the population standard deviation. Okay? Remember, this is the population value. So that's the population standard deviation divided by square root of sigma, and therefore I have the standard error, or in other words, the standard deviation of the sampling distribution. The sampling distribution standard deviation. Now because it's a divide, because I'm dividing by n here, notice that the value here, the standard error, is going to be smaller than the population standard deviation. And if you remember what we saw just now there, that was one of the points we made in the examples we gave just now, where the variation or the variance of the standard error, the variation or the variance of the sampling distribution is smaller than that of the population distribution. Okay, so that's point number 2. Keeping that in mind. So, next point. If the population distribution is normally distributed, if the population distribution looks like a normal distribution, then automatically the sampling distribution will also be a normal distribution. Right? So the population distribution is normally distributed, the sampling distribution is also normally distributed. Now, however, if the population distribution is not normally distributed, remember we gave an example previously that where the population consisted of just 5 people, it was square, right? So it's not normally distributed. Now, if the n, the sampling distribution, the size n, which is the sample size, if it's large enough, then the sampling distribution will be normally distributed regardless of what the population distribution looks like. Now this is a very powerful point. It says here that it doesn't matter what the population ends up looking like. It could be a square, it could be normally distributed, it could look like a whole bunch of funny waves, okay? But the point being that if the sample size I pick is large enough, let's say 30, and I collect random sample groups of size 30 inside there, and I form a sampling distribution, if my n is large enough, my sampling distribution will end up also looking like a normal distribution, even though my population distribution doesn't look anything like it, right? So very important point here. So these are the 4 points. Again, first point, the mean of the sampling distribution is the same as the population mean. The standard deviation of the sampling distribution is known as the standard error, and is calculated by taking the population standard deviation divided by square root of n, where n is the sample size. If the population distribution is normally distributed, it doesn't matter what sample size I pick for the sampling distribution, my sampling distribution will also be normally distributed. If, however, my population distribution is not normally distributed, if my sample size n is large enough, we'll talk about how large is large, then the sampling distribution will be normally distributed even though the population distribution is not normally distributed. Okay? Now, these points here probably might take a while to sink in, but try to think about them, then we'll move on. These set of graphs here are going to illustrate the last point about the central limit theorem. The idea here that if the normal distribution is not normally distributed, or whatever it looks like, okay, if my n, the size of my sample group, is large enough, then my theoretical sampling distribution is going to be normally distributed regardless of what the population distribution looks like. Now this is obviously a square distribution. This one is bimodal, it's got two humps. This one is skewed, it's skewed to the left, a lot of outliers, and this is just a standard normal distribution. Now if I have all these as my various population distributions, this is what my sampling distribution is going to look like for a sample size of 2, right? Where each of the sample groups I take is only a size of 2. Now if you recall, this guy here is just what we showed just now in the example of the 5 patient distribution, the 5 patient population distribution, and we got a sampling distribution that looks like a pyramid. This one looks a bit, well, a bit like a hump. This hump here is starting to become less sharp, and the normal distribution, the normal population distribution looks just as normal in a sampling distribution. Except for one important point. It's tighter. The spread is tighter. Remember that fact that the variance, the variation of the sampling distribution is smaller than the variance or the standard deviation or the variation of the population distribution. Now let's increase the sample size from 2 to 10. Now from 2 to 10, if you've noticed here, they all start to resemble much more like a normal distribution. Now this is even though the population distributions here look nothing normal. In particular these two, they look nothing like normal distributions, and yet by the time sample size has become 10, they are starting to look like a bell curve already. Because as I increase the sample size further, now they really resemble normal distributions, right? These are normal distribution bell curves, where all of them, by the way, have variations smaller than their original population distribution. Okay, I hope this set of graphs help to illustrate this idea about the last point of the central limit theorem, where the final sampling distribution will be normally distributed regardless of what the original population distribution looks like. Now we're going to talk about why this is important in a moment. Just now we mentioned that we'll talk about what sample size is large enough. When we say a large sample size, before we can invoke the central limit theorem and say that the sampling distribution is normally distributed regardless of the normal distribution. Well, traditionally we set the cutoff point at 30, right? You see this number appear often when people talk about how many samples do you need to collect, and often you will hear them say you need at least 30, and that's where this comes from. This is the traditional. Now don't ask why it's 30, it's just what's traditionally used, meaning someone started off in the early days of statistics saying 30 is enough, and we have continued on, right? So sample size of 30 is traditionally used as the cutoff value for saying this is large enough to invoke the central limit theorem. And so regardless of what the population distribution looks like, if you have a sample size of 30, then your sampling distribution will be normally distributed. The actual sample size you actually need to be large enough, right, to invoke this central limit theorem actually depends on the skewness of your population, how skewed your population is. For example, one of the 4 example population distributions we saw just now, the third one was skewed to the left, if you remember, right? Now the more skewed it is, the more samples you need for the sampling distribution to actually look like a normal distribution, right? So the more skewness, the higher the sample size you need. If it's not as skewed, then obviously you need less sample sizes. One last point, as the sample size increases, the variability of the sampling distribution also decreases, right? So as the sample size increases, the variability of the sampling distribution decreases, or in other words, your sampling distribution is going to become more and more narrow. And this should be obvious, because as your sample size increases up to a point, the sample size, okay, equals to be the size of the population. Sounds weird, right? Let's say a population was 1 million. That's huge. Now I could also say, assume I go and take a random sample of 1 million people. Alright, that sounds very weird. That's not really a sample, but I could do that. So that I increase the sample size, and suppose I increase where the sample size is exactly equal to the population size. What is my sampling distribution going to look like? Right? My sampling distribution is going to look like, what do you think? It's going to look like a straight line, right? Why? Because when I collect 1 million people in my sample group, where this 1 million people is actually the entire population, then as I collect different how many variations of 1 million people can I take? When I take different variations of 1 million people, I'm still taking the same 1 million people, and so when I calculate their sample mean, I'm actually calculating the population mean. And so my sampling distribution is just going to be population mean, population mean, population mean, population mean. In other words, it's going to be a straight line, right? Variability, or the standard deviation, or the standard error, is going to be 0, right? And if you remember, there's another way to look at it. How do we actually calculate variability, or how do we calculate the standard error, right? Remember, it was standard deviation divided by square root of n. So it should be obvious that as n goes up, the standard error goes down, or the variability goes down as the sample size goes up to a point where the sample size is so big that the standard error becomes almost 0. Okay, so these are the points about the central limit theorem. Now let's try to summarize. We are not actually generating a true sampling distribution. We are not actually trying to measure the true sampling distribution, because to do so would mean we have to take many different samples. Or in other words, we have to take many different groups, randomly selected groups, and out of each of these samples or each of these groups, we calculate the means of all of them, the sample means, and from there generate the true sampling distribution. We are not doing that. We are not doing that. It's not practical. Instead, we decide on a criteria which satisfied the central limit theorem, where this criteria, one of the basic ones, is a sample size of 30 and greater. So we decide on this criteria and argue then that if we follow this criteria, then the sampling distribution is known, right? We know what the sampling distribution is going to look like. It's going to be normally distributed, right? And we know what is the perhaps we may know what are the different parameters about this particular sampling distribution, where they are the standard error and the mean of the sampling distribution, right? Now, in this case, to generate the standard error, we need to know what is sigma. Sigma is just the standard deviation of the population distribution, or the variability among individuals. The standard error then is sigma divided by square root of n, which is the variability among sample means. Or in other words, what is this variability among sample means? It's just a way of calculating, or a way of saying, if I have different samples or different groups, where let's say I have 10 different samples or 10 different groups, how much do the sample means, or the means of each sample, differ from one another? If the standard error is very high, right, then the sample means which I calculate may vary from each other quite a lot. If the standard error is very low, then the means of each sample, or the sample means of each different sample, will vary from each other by very small. And as we learned about just now, as the n grows larger, right, not this n, the sample size, if my sample size becomes bigger, then my standard error becomes smaller, which means that if I take 10 different samples or 10 different groups, the means of each sample, or the sample means, will vary from each other by quite a small amount, right? Simply because my sample size goes up, standard error goes down. Now, another reminder once again, the sampling distribution pertains to the means of samples, right? Not individuals. The sampling distribution is the means of different groups, different randomly selected groups, and not the individuals themselves. So remember, we were talking about earlier in the earlier lectures about mean plus minus 2 standard deviations, and we said that in between this particular range of mean plus minus 2 standard deviations, if it is normally distributed, lie around 95% of all individuals, 95% of all values, 95% of all individuals, right? We can also do the same thing for the sampling distribution, where in this case, it's not x bar, it's x bar bar, right? Or the mean of all the sample means. So this x bar bar plus minus 2 standard errors, 2 standard error of the means. We could also say that it will also be a sampling distribution here, and then we have two bars here where it's the sample mean of the means, plus minus 2 standard errors, and the area in between here is not 95% of all the individuals. It's 95% of all sample means. Okay? Remember, sampling distribution pertains to means of samples. It pertains to sample means, not individuals. Means if I go out and I collect multiple different samples, multiple different groups, right? 95% of the time, the sample means which I calculated from the groups lie between this interval. If I go out and collect random individuals, then 95% of the time it will lie within this particular interval, right? The interval is 95% of the sample means is not the same as the interval of 95% of the individual observations. They are different. This is a much smaller interval compared to this one, right? Because this value here is smaller than this value here, right? The standard error is smaller than the standard deviation of the population. This value here and this value here, however, are usually the same in theory or very close to each other in practice. So how do we use the sampling distribution in practice? Or in other words, how do we apply this standard error? Now, when we do our hypothesis testing, when we do our statistical tests, almost always we are comparing means of samples. We are comparing sample means rather than individual observations. Meaning, in the previous lectures, when we did all these examples about calculate the probability of finding an individual where its height is less than whatever, or his blood pressure is more than, or his weight is in between this and this, this is just academic. This is usually just for practice. It's just practicing your theory, right? When we do actual research, we almost never calculate probabilities for individual observations. We are almost always trying to calculate probabilities or doing hypothesis testing, we'll talk about that later, of samples, right? Of sample means, which means we need to work on the sampling distribution rather than the population distribution. Now, how does this affect the critical ratio that we talked about earlier? Critical ratio here meaning z, where it's x minus mu over sigma, right? This was for individual observations. What is the purpose of calculating this critical ratio or this z-score? It is to convert the values that you have to the standard normal distribution so that you could use the log tables. Now remember, that's all it's for. If you don't want to use it, you can calculate it manually using Excel, computer, or whatnot. Now, we can do the exact same thing for sampling distributions, except this has to be modified slightly. Now, so for the z, or the critical ratio for sampling distribution to be converted to a standard normal distribution is exactly the same thing, except now instead of x, where it's an individual observation here, now the x here is an x bar, or it's a sample mean. There's no longer individual observation, it's a sample mean, minus, it should be x bar, which is the mean of the sampling distribution. But if you remember previously, the mean of the sampling distribution is the same as the population mean, so this can still remain. X bar minus mu divided by, now it's no longer the standard deviation or the population standard deviation, it is now the standard error. And remember what the standard error? The standard error is sigma, or the population standard deviation, divided by square root of n, where n is the sample size. Okay, so this is the new formula for the critical ratio, the z. And remember, the only reason for doing z is so that we can convert to the standard normal distribution so that we can use the log tables, right? Or else you could do the exact same thing, which means use a computer to calculate the exact probability values for whatever you're trying to test. Now let's go through some examples so that we can gain some familiarity of working with the sampling distribution. So let's start. Given that the population blood pressure, so the population mean here, let's say that we know it, it's 120 millimeters of mercury, and the standard deviation, the population standard deviation, or sigma, right, is 10 millimeters of mercury. So here, mu is 120, sigma is 10. Now if we take repeated samples of 25 individuals, or we take samples of where the sample size is 25, what proportion of all these samples will have mean values greater than 120 millimeters of mercury? Now, look at this. It is almost the equivalent of me asking the population distribution type question, except a population distribution type question would have asked if the population blood pressure mean is 120, standard deviation is 10. If I randomly pick an individual, what proportion of individuals would have blood pressures above 124 millimeters of mercury? And you could probably do that easily. Now that it is for sampling distributions, now we are saying so for if we take repeated samples or repeated groups where the sample size is 25, what proportion of the samples would have their sample mean values above 124 millimeters of mercury? Okay, the only difference is in the wording here, because now we're working on the sampling distribution. We are no longer working on the population distribution. However, the method of doing it is exactly the same. So pause for a moment and try to do it. Okay, we still calculate the critical ratio or the z-score, right? And the purpose of doing that is so that we can use the log tables. So we have, what do? We have x bar here is 124 minus of mu is the mean, 120, divided by standard error. Standard error is sigma population standard deviation divided by square root of n, where n is the sample size. Okay, work all that out, you get a z of 2.0. And we're asking for greater than, so that's z greater than greater than 2.0. If you look up inside your log tables, that should be about 2.3% of random samples. Okay, so that's your answer here. Next question. A physician wants to detect adverse effects on blood pressure in random samples of 25 patients. He decides that a mean blood pressure in the upper 5% of the distribution is cause for alarm. What is the threshold value? Now notice the question here differs quite a bit from the previous one. However, the method of doing it is almost the same. But let's talk about what this actually means. Now this physician wants to measure a particular group of patients. Now let's assume for now that the patients possibly in normal conditions would follow blood pressure similar to that of the general population, which is given here. Same as the previous question, where the general population, your mean blood pressure is 120, standard deviation is 10. Okay? Now, sometimes, right, this physician is worried that his group of patients, this population of his patients that he's looking at, possibly have higher blood pressures than normal. But he can't measure all of them constantly, because that would be a waste of time. So he decides to take random samples of 25 patients at a time, and he decides that he's going to get worried if the mean blood pressure that he calculates out of a sample of 25 patients that he measures, if this mean blood pressure goes above the upper 5% of what he expects, assuming that the normal population's mean should be 120 millimeters of mercury, where the standard deviation is 10, right? If he calculates a sample mean that exceeds this, then that's cause for alarm. So, what is this threshold value? What is this value? What is this sample mean that would exceed this upper 5% of the distribution? Right? So if you think about it that way, you're actually trying to do the same thing as previously, also calculating a z-score, except now you're trying to find out what is the x bar. What is the x bar, or the sample mean, that would trigger this particular condition, where this sample mean of this 25 patients would be greater than 5% of the sampling distribution given these parameters, right? So pause for a moment and try to do it. So as mentioned, the method of doing this is actually about the same. You still have the z value equals x bar minus mu divided by standard error. So standard error part, mu part doesn't change. What changes now is you're given the z value, where the z value is the value of z which contains 95% of the data on one side and 5% on the other. If you look up the tables, that's 1.645, right? And from there, you try to find what is x bar. So it's just a matter of algebra, and you'll find that x bar is 123. So in other words, what he's saying here is that if the normal population has blood pressures of 120, standard deviation of 10. If this physician goes out, gets samples where the sample size is 25, if the sample mean exceeds 123, this is cause for alarm, because 95% of the time for a normal population it should not go above this value. Third question. The physician now is trying to decide his sample size. He decides that 90% of the time the mean blood pressure of his samples should not rise above 120 millimeters of mercury. How large should his sample size be? Now once again, the given parameters as of the previous questions don't change. In other words, the population mean is still 120 and the population standard deviation is still 10, right? So the method of doing this is still the same. You still calculate the z value. What's different, however, is that now you know the mean, now you know the threshold which you're trying to hit for, which is 122 millimeters of mercury. You know the z value, where the z value is based on this, the 90% of the time part, right? And you know the standard deviation. What you do not know, however, is sample size, or n, right? So think about it for a moment and try it out. Pause this and give it a shot. Okay, as mentioned, it's exactly the same formula as before. You know the threshold, 122 minus 120, which is the population mean, divided by standard error, where the difference here now is that you know the population standard deviation, but you don't know the sample size. You're trying to find it out. The z value here is based on this, 90% of the time. So you look for the cutoff value where one side is 90%, the other side is 10%. And from the tables, that would be about 1.28. So once again, using algebra, you end up with n equals 40.96. Now, obviously, the sample size cannot be 40.96. It has to be an integer, a round number. So the question is, do you go to 40 or do you go to 41? Now, you do not just round it up. It depends on what the question is asking. And so the question says that the mean blood pressure of the sample should not rise above 122, right? So if you're trying to work this out, give it a shot. This time make this the unknown and replace n with either 40 or 41 and see what the value here is. And you'll find out, probably, if you do it correctly, that for an n of 41, the value here, or the threshold value, is below 122. And if you use n equals 40 on the other hand, the threshold value here is higher, or slightly higher than 122. So the correct value here should be 41. Alright, question 4. It is given that PO2, or the partial saturation of oxygen, in healthy adults has a mean of 90 millimeters of mercury and a standard deviation of 7. Right? So now we're looking at something different from the previous questions. What proportion of individuals are expected to have a PO2 between 83 to 97 millimeters of mercury? Assume normally distributed. Now, notice here we're talking about individuals. So actually we are going back to the previous lectures, the early days, the z value calculations, or the critical ratio of the early days. We are working on the population distribution now. We are not working on the sampling distribution. Okay, so this should be much more straightforward. Just to keep in mind that it's not always the sampling distribution. So pause for a moment and give it a shot. Okay, so since it's the population distribution, we can go back to the simple form of the critical ratio, or the z value, where it's just x minus the mu divided by sigma, or the standard deviation. Now the only other trick here is that we are asking for the, you're looking for the range this time. And there are a couple ways to do this. You could first calculate the lower limit, and then you could calculate the upper limit. So in other words, 83 here, then 97 here, minus the mu and the standard deviation, and find the z. Or you could just notice that this is actually just 83 to 97 is just 90 plus minus 7, and 90 so happens to be mean. So in other words, it's mean plus minus 1 standard deviation. Okay, and if you know that and you look up the table, or in other words, that's just z equals 1, that you will find out that it is 68.3% of the healthy individuals. Okay, straightforward.